আমি বলছি যে আলিরা ওই 12:30টার সময় না সবাইকে বলবেন একটু ওই এদের ঘরে আসতে। আমি তো সুদীপদা শ্যামলদাকে বলে দিয়েছি, ঠিক আছে, নন্দও জানে, ওই বাকি যারা একটু নিচে আছে একটু ইন্টিমেট করে দিন। হুম, ঠিক আছে। হ্যাঁ, হ্যাঁ, 12:30। হ্যালো, গুড মর্নিং।
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am.
Okay, so I will start today the NMR.
Excuse me, ma'am.
Yes.
Ma'am, the assignment that you have sent, which you
No,
have to
no, I
submit
just
on
click and
28th
click it.
February.
No, no, I did rectified and flow in my classroom, not in the exam.
No, ma'am, before that, you had given one assignment before the midterms.
Before the midterm, I gave theoretical assignment, na UV
Yes,
visible.
ma'am. And that you have to write in A4 size paper or any.
Oh, any paper, that's not a problem.
Okay.
Anything that visible, I can, the visual clearance is needed.
Okay.
Okay. Okay. So, nuclear magnetic resonance. Have you any idea about this one, nuclear magnetic resonance? And actually, we use the term NMR popularly, and we are more familiar actually NMR, not like nuclear magnetic resonance all the time. Any idea? Hmm? Anybody? Any idea? What is NMR?
No, ma'am. But I can try to guess.
I guess just magnetic. So it's like you need some magnetic parameter. And these magnets are resonate, and it in the nuclear key around nucleus. So this is something we actually will use for identification of compounds, and this is a non-destructive process. But and we can use we can recover the sample from this uh, NMR after the application analysis of NMR. But one point is needed. This one we need some solid sample. We can use solid sample nowadays. Previously that was not possible. Nowadays we can use direct solid sample and also the in solution phase. But the solution in for making the solution we use the solvent, deuterated solvent, not the protons in normal solvent. Like we don't use the chloroform CHCl3. We use chloroform in deuterated form, that is CdCl3. So from here, first, how to make the sample preparation. From here, you can guess that we need the analysis in a totally deprotonated environment where the proton in the solvent. So proton have some role. That is, you have some significant role from our proton in the molecule. Slowly we will go. We will not just one day. If it will take 2 and more day, we will go. Okay, because question may be very simple, but thought is very important for you because NMR is a very popularly and most useful tools for identification of compound, not for only organic compound, phosphorus, phosphorus based, sulfur based, chlorine based compound you can identify it from the NMR. Now spectroscopy, this spectroscopy is a powerful tool generally with only three pieces of data: empirical formula or percentage of composition. We can find infrared spectra for the functionality, and NMR spectra. A chemist can often figure out the complete structure of an unknown molecule if they have these 3 point values. Now, formula gives the relative number of carbon and hydrogen and other atoms. Infrared reveals the types of bond that are present. NMR reveals the environment of each hydrogen and the relative numbers of each type. So NMR in very one or two words means it reveals the environment of hydrogen, presence of hydrogen in which environment, and the number we can guess from the NMR. So combine all these, we can figure out the compound. Types of informations from the NMR spectrum. Each different type of hydrogen gives a peak in different type or group of peaks multiplied. The chemical shift gives a clue. There is a term we will learn it slowly. The chemical shift, the whose unit is we can write down is delta, or sometimes we write down like delta values in ppm, gives a clue as to the type of hydrogen generating the peak: alkane, alkene, benzene, and aldehyde, etc. So alkane hydrogen peak are different from the alkene because the hydrogen present in the environment are different from each other. So we can identify alkane and we can identify the alkene depending on their chemical shift value. Okay. The integral gives the relative numbers of each type of hydrogen. Spin splitting gives the number of hydrogen on adjacent carbon. So this point, the blue points, we will clarify little slowly. The coupling constant, that is also a very important uh, coupling constant, or you can write down J Hertz, also gives informations about the arrangement of the atoms involved. So whether like suppose you have alkene, these are trans or cis, the protons, for protons are cis and trans orientation, that can be actually understandable from the coupling. So coupling between this proton gives a different value, and these values we can calculate it from the NMR spectrum, and we can conclude whether it is trans or cis orientation. So this very important significant part actually we can achieve, we can describe from this one and identify the compound. Now the proton. Although interest is increasing in their nuclei, particularly C13, the hydrogen nuclei is studied most frequently, and we will devote our attention to it fast actually. Okay, so there is a different type of nuclei, but we concentrate hydrogen nucleus and C13, not the C12. These two. So you can understand there should be some unpaired electron. Now, the nucleus is a charged particle in motion and so behaves in a similar fashion to a simple tiny bar magnet, like this. It will develop a magnetic field. In the absence of magnetic field, these are randomly oriented, like this way, no field. Okay, it looks like. But with field, they orient in a particular position because of the north pole south pole interaction or etc. whatever. Otherwise, not like this. Now, in the presence of an external magnetic field, two spin states exist that you always know, plus half and minus half. The magnetic moment of the lower energy plus half state is aligned with the external field, but that of the higher energy minus half state is opposed to the external field. Okay, these will some energy spin energy state. So that is higher, and that is higher energy level, and that is lower room temperature level or little lower. So spin quantum numbers of some common nuclei, the most abundant. What is spin quantum numbers? Just in qualitative idea. Spin quantum
Orientation of spin of electron.
position, whether it is aligned with the field or not, plus or minus up. That is actually quantum orientation of the electron in a cell. Okay. So, in a qualitative idea, so this spin quantum number we have to calculate. For why we are taking few nuclei are you can say participate in the NMR spectroscopy, not all. Even why not C12? C13 we will consider, but not C12. So we need some unspin or odd mass, okay? Or the spin number state actually should be odd. Odd atomic number have the property of nuclear spin. Something should be free actually, so they can interact with the other environment and we get some knowledge. So proton is minus half, number of state is 2. That is the number of state actually depending 2I plus 1. Okay, total number. This is deuterium 1 spin. So half is 13, 13C is again half. 14 N not possible for NMR. 16 O not possible. 17 O is possible. Then 19 F is possible. So in this way, a different type of elemental base NMR is possible depending on the probe also. So there will be some instrumental setup we have to change for the proton. Proton and 13C you can do at a time. That is now the instrument are upgraded up to this. We can find out both, but these are very specific. We need some different type of probe for this analysis. Okay. So nuclear spin energy level, I already mentioned. These are aligned with the actually applied field. So it's stable, aligned, so stable, plus I. And if it is minus, that is oppose the applied field and its energy level is higher. Just in a pictorial presentation. So absorption and energy, what is absorption in energy? So this aligned position can be transformed to this one opposed, and that is actually delta E is equal to h nu. This is radio frequency that actually we count by its resonance. So it's moved to up and we resonate or we irradiate the molecule with radio frequency such a way they resonate in particular way and coming down, so that we can measure is this value actually. Okay, this is some parameters. Now, energy separation depends on B0. Degenerate at B0. Okay. So, B0 increasing magnetic field strength, and these are not so much important now. This is for NMR. I just keep this one too because we don't need also parameters. I will send this one for you. Just go through one time with the books, but not all are important. Or if we go to the in depth, so that you need more physics than chemistry. So we focus on the chemistry part more. From here, the idea about the identification and for this one, whatever we needed, we will just go through. But I will send whatever I prepare. This is in general presentation. So resonance frequency of the selected nuclei. Here this isotope abundance is very important, and that's why I want to share this slide. Now proton is 99.98% in each molecule. Then, but you see this one is less. Even 13C is 1 point something. So whatever, if you want to go for the frequency to resonate the proton, that takes few minutes to identify the peak. But sensitivity is higher for proton because its abundance is 99.98%, almost 100%. But 13, if you want to get the peak from the 13C, then you will get 1.108% abundance, and you need, suppose for proton you need maybe 2 seconds, but for 13C you need at least minimum actually 24 hours run. So multiple scan will be there and all the scanning you get the information for the 13C etc., and then multiply with the system recorder system, and you will get the response. You can see the response. So because of the low abundance actually, you will get 13C in a for long after the long run in radio frequency level. Okay. Now, but 19F is also 100%, so you will get immediately. If you have that fluorine probe for NMR, you will get immediately if you have either fluorine you have or not. So it's easy. And actually fluorine detection in anywhere nowadays is going through the NMR because it's very sensitive, and even the sample don't need to go for any modification, raw sample you can use. So that's why. So proton 19F is very easy to detect with respect to 13C. It needs more even like number of, if the molecules are long range and long molecular weight polymeric sample, you need more time, even 3 days sometimes. For suppose you have polysaccharide cellulose, you need 72 hours for the run the sample in NMR instrument. It's time consuming. Okay, this one I just see. Okay, so next one. Okay, now from here. Okay, from here, not like this one. Just give a look on this one parameter. So this is the fortunately different types of proton proceed at different rates in the same magnetic field. Different, whatever the difference. So what is the different type I mentioned? I just give one example first to understand. After that we will go for chemical say. Suppose here is the CH2. This CH2 is identified in NMR, but this CH2 present in a different environment from the CH3. Okay, from the CH3. Then because of this actually their peak level, their resonance energy may be the same, this one megahertz, they can resonate within themselves. Okay, but in presence of applied field there will be difference. Then that is actually chemical shift. We will see how this one. Now chemical shift. Now for chemical shift measurement, that is actually most fundamental thing for like chemistry, for organic people to identify the proton environment. Most important thing to identify the position. But one thing we now introduce here, the some standard we need, because in such a standard, suppose there is a delta scale I already mentioned, we measured the chemical shift in a delta scale, delta in ppm. So delta, where the scale will start show the zero and where coming actually. So we need to identify such sensitive, the molecules should be so much sensitive that it actually shows high intensity of proton at a time, and that makes we zero. Okay, by trial method is identified one sample which are popularly used as in standard. This is maybe you can do internally or externally, no problem, in such a way that its value is fixed, peak of nature is fixed, and you place this peak at zero, then you calculate the other. Why this will happen? Now see the structure. This is trimethyl this is TMS, actually tetramethyl. Then there is a 4-methyl group. This 4 methyl groups are identical because they are separated by Si, and Si has no role for electron withdrawing, inductive effect, a resonance effect, interfere with this carbon hydrogen bond. Because here we see the electrons which are moving, actually their alignment are ups and down because of the presence of chemic environment. Actually here 4 methyl group present in a same environment. Okay, and they are like all carbon hydrogen are distributed equally. So how many hydrogens is there? 1 3 3 3 12. 12 hydrogen resonate at the same position, so it's so sensitive and it gives a large peak. You need very small amount, and this tetramethylsilane is located. We actually the scale standardized, first run the TMS and set the 0. Okay, the TMS is coming here, this one. But sometimes it forfeit. If you go for the externally, first you run the standard sample, you set the 0. But how can you understand how far from the sample proton from the 0? If you not in that your sample, you not introduce the TMS as internal standard. Okay, so TMS used as internal standard for each run of any known unknown molecule, known or unknown whatever. Then, and it is fortunately actually TMS peak never collide with any other coupled or any other proton. It coming always in 0. So we set the 0 and then identify the rest are coming where, and this delta scale is 0 to 10. Within 0 to 10 we can calculate actually in this way. Now this TMS should have some special role for use as internal standard. What is these roles? First, TMS when we used as internal standard, so that it should be so much inactive, they not interact with the chemically interact with the molecule for which it used as internal standard. That should be remembered. Okay, so it's non chemical actually TMS is inactive or inert compound. Okay, stable inert compound, not react with any molecule in such way. So that is something good characteristic for TMS. Second characteristic, it's stable, its stability, this tetramethylsilane present in this structure in higher temperature too, because we need some temperature upgrade, uplifting of temperature in some study till time 80 degree. Suppose you have proton, so in a ketoenol tautomerism, so there will be hydrogen bonding, but you don't need hydrogen bonding identification, because if there is a hydrogen bonding, the shifting will be little bit shifting, chemical shift is there, because hydrogen are now bonded with by hydrogen bonding. Okay, so in that case, we need some temperature. So up to 80 degree, there the disappearance of hydrogen bonding, and there is only keto and hydroxyl group. Okay, so in that case, if we use the TMS, not if TMS not stable at higher temperature, then your experiment will be failed. So TMS is stable at high temperature, is inert, it has non-hygroscopic, it has no fascination for water, and even it has no fascination for assemble the molecules. So it's inert. So not react, not assemble. So that's why, and another point, it's soluble in all deuterated solvent. That is another important part. This is soluble in all deuterated organic solvent. D2O, D2O is a, or in even D2O2. D2O means water. We can't use the water in NMR. We need D2O, deuterated water. They are also TMS is soluble. So that is a very important characteristic for TMS for choosing it as internal standard for NMR. Okay, so that is the structure and it plays as a 0. Chemist. Achha. Next. Now, that is actually just some presentation. So TMS 0 to the up to this one is the shift in hertz. This is the shifting. This is known as, this is down. Why it is downfield? I am mentioned here downfield. So this is the TMS where the field is intact. Magnetic field we applied and there are only six protons. Now the applied field energy is consumed slowly actually. Okay. First 0 and then if we coming down this scale actually, then what happened? That means the energy is slowly consumed by the absorption or shifting of the spin between the spin. Okay, plus up to minus up. So this consumed actually means downfield. So few only TMS proton actually in the applied field resonate. After that, all protons resonate in the lower energy in applied field. Slowly it consumed actually. Okay, and that's why this is downfield means down applied field or decreasing the down applied magnetic field. That is the meaning actually. Okay. Now, the shift observed for a given proton in hertz also depends on the frequency of the instrument used. Okay, instrument that will some mathematical calculation next today or I will go because it's not easy to understand initial part. Okay, higher frequency equal to large shifting hertz. This I already mentioned. This one actually, this instrumental means there is a 60 megahertz instrument, 120 megahertz instrument in this way. So the value of this and these all are related to the applied magnetic field. So depends on this one, we can get the actual shifting will be little bit different. But without TMS, we can identify it. With respect to TMS, we can identify it. Now chemical shift in another form. You have actually chemical shift and spin multiplicity concept very nicely will gather actually. These two part is qualitative idea for NMR spectroscopy to analyze the organic molecule. So you need chemical shift, a little bit coupling constant and spin multiplicity to understand and that from here you have some questions. So I just focus mostly on the part which are related to analysis for the organic molecule. Okay, I will repeat the same with a different presentation next. Okay, today in different ways so that you go through this one. The next day you can at least answer something. Otherwise, you never understand actually. Okay. The chemical shifts from TMS in hertz are bigger in higher field. I already mentioned instrument 300 megahertz, 500 megahertz. Then they are in the lower field instrument. Okay, shifts from the TMS. Why? This one. So they input these instruments, suppose 300 megahertz and 100 megahertz. So 300 megahertz input the magnetic field higher. So that after the TMS resonate, they coming to the next proton. If the frequency applied magnetic field is different, okay, then what happened? It resonates later on. But if has a sufficient energy actually, field means energy, magnetic energy, that it resonate in higher field. Higher means one means towards the TMS, not apart from the TMS. Okay. So that is some their tentative value within the range, but more towards the TMS. The peak will be more towards the TMS. Okay, that is the concept. We can adjust the shift to a field independent value. The and now we can make it independent. with the instrument used. How we can do this by equation? Chemical shift is equal to delta. Now it is the delta actually when it's not depends on the instrumental magnetic field. It depends only the separation of the TMS to the this one. So this is shift in hertz divided by spectrometer frequency in megahertz. Whatever the value you get, that is actually in ppm, and it is actual the proton NMR peak. So now first we introduce chemical shift is the difference between the TMS and the at the resonant with the applied magnetic field up to this. Now what happened? There is some difficulty arises because of the energy, applied magnetic field is different for different instrument. For sophisticated instrument like 300, 500, and for lower instrument 160 megahertz. That is. Now, if we erase these limitations by dividing introduce this part, the instrument spectrophotometer frequency is megahertz, immediately you will get only some number which can be actually abbreviated by ppm, parts per million, because megahertz is the 10 to the power 6 into hertz. Okay, so that's why we get a simple digit, and this digit is fixed for 300, 500, whatever 100, 600. Okay, the type chemical shift is fixed then if you divide it by like this way. So that is some neutralization so that each instrument gives the same frequency for a same proton. So this division gives a number independent of the instrument used. A particular proton in a given molecule will always come at the same chemical shift. Constant value will be there. Okay, so it's some rectification. Now, this that's actually some calculation for clarification. Proton operating frequency instrument, this one, Hertz equivalent, this one. So this is actually up to this much 60 hertz. So each ppm unit represent either a 1 ppm change in B0 magnetic field strength Tesla or 1 ppm change in the precessional frequency megahertz. Okay, so this actually the difference. What is the difference between actually the scale 0, 1, 2? So this is the difference 60 hertz. So this is the hertz or this way. Now 1 parts per million of n megahertz is a n hertz equal to n megahertz into 1 by 10 to the power 6 is equal to n hertz. That we can parts per million ppm. That's actually. Okay, so what is the scale actually defined? This scale defined if the instrument is 60 megahertz, then the hertz, this 60 hertz is the difference between this 1 and 2. If it is 100 megahertz, then the distance between the 1 or 2, 0, 1 or 2 or 3 is the 100 hertz. Okay, in this way the scale are maintained. That's why we divide this thing. Okay, and we will get a fixed value. Now NMR correlation chart. Whatever I have mentioned that you have some different proton have appeared in a different region. Now we will go later on in more complex way. But here at a look, how we will predict actually with respect to TMS. So this is the TMS, and this is TMS, and this is I write down here upfield means magnetic applied magnetic field started from here. After that is scanning and resonate, and it slowly losing its efficiency or energy. Okay, and it is the downfield. And whatever the upfield, right, just below I mentioned shielded and deshielded. What is this mean shielded? What is the meaning of shielded? Shielded means suppose TMS. I just go again for this one. This CH proton, this proton chemical environment here carbon, silicon, and this one. So this proton, each proton actually, they have no effect actually for withdrawing or donating effect. They have their electron with them, so they are shielded. Can you get the point? What is shielded? So they are shielded with their own electron cloud. But if there is any chance environment will be different, there will be chance to attack the electron towards, suppose you have some electronegative minus I group aside. So what happens? The electron cloud is going towards them. So these protons slowly descended from their proton, from their electron cloud, and this electron cloud is deshielded. That means it resonates later because it needs, it's not the same energy level. They can applied magnetic field when coming to the deshielded energy level, then it will collide. Okay, and NMR peak will come. It's clear.
Yes, ma'am.
Little bit, we will go through little bit na first time. So I just this is some browse of the NMR whole, not like I'm started, just some browsing. What you just go through the initial introductions from book. Okay, so this is shielded and this is deshielded. So that means shielded proton gives low delta value. You see delta value is 1, 2, 3, 4, 5, etc. So shielded proton gives low delta value and deshielded proton gives higher delta value. Now check one example. Suppose you have this one. This one is a saturated moiety. So all proton, there is a no pi bonding, etc. So all proton are like shielded with their electrons. So they are in the this level up to this one. Suppose you have aromatic CH2 and aromatic. So there is a some resonance energy. Then the electrons are not with them. Cloud is distributed with the aromatic moiety or distributed with the some nitrogen moiety, sulfur moiety, triple bond, etc. In that case, you have the value is downfield shifted toward deshielded, and you will get the higher delta value with respect to, this is sp2 proton actually, with respect to sp3. Okay. Now suppose we have CHO aldehyde. So what happened? This proton, the environment is different from the this carboxylic acid group. Carboxylic acid group, these proton are attached with the OH, and this proton attached with the carbon. So both the different. Now which one is more deshielded? Because this one is more deshielded. Okay, this one is more deshielded because it's directly attached to the oxygen, it directly not attached to the oxygen directly. So electron withdrawing capacity for oxygen is higher in carboxylic acid group. So these proton have more deshielded with respect to aldehyde and its value is higher than aldehyde. And you can get 9 to 10. If your peak is 9 to 10, then you have aldehyde group. If you have 11 to 12, then you have different proton. Okay. So deshielded, this one anisotropic, I am not want to right now want to share actually because you have not is our different concept. So that is actually just in deshielded electron. Suppose you have chlorine, deshields the proton. Chlorine, electron negative element, it pulls the electron cloud towards itself. So now proton are deshielded. I just showing some presentation like this way, that it towards the chlorine. So it gradually deshielded actually, and its reflection you will get in the downfield shift or higher delta value in NMR. So chlorine deshields the proton, that is, it takes valence electron density away from the carbon, which in turn takes more density from the hydrogen, deshielding the proton. So it's a sequence here. So first cloud changed carbon towards the chlorine and then proton towards the carbon, or this is a dragging force. So desealed proton appears at low field means down field, or highly shielded protons appear at the higher field. Deshielding moves proton resonance to the lower, because lower field means now the consumed. Slowly the applied magnetic field consumed with the interact with the molecules proton peak. Okay, and when it coming to the low field, because it's down field already shifted, the resonance value is needs, there is a resonance actually. Okay, so this value actually, whenever the applied magnetic field energy is a merge with the proton desilted proton frequency, then it resonates and we will get the peak of energy. That is the concept actually. Up to this is clear? Little bit maybe. Suppose here I am giving one example. Suppose you have compound CH3, মানে CH3 X. X, I just changed the X. F, OE, Cl, Br, I. Then element this way, and electronegativity of X is, I write down 4.03, role of electronegativity or role of the element. 3.1, etc. Then you can see the proton value. This CH3, the 3 proton value actually will get for a higher electronegativity, will get for 4.0, for after that 3.4, 3.05. So that is the, this CH3 is the most shielded proton. Most shielded proton. Is clear what is shielded and what is deshielded?
Yes, ma'am.
Okay, so that is the environment. So this proton in the CH3 proton, the chemical environment is different from the CH3OH proton, this proton, methanol or chloroform. And this will give different peak in the NMR spectra or delta value in NMR spectra depending on their shielding and deshielding nature with the applied magnetic. Clear up to this? If it's clear, then it will be easy to understand. We didn't need to go so much about the physics part, just to understand what is the strategy or what is the role of these stability factors you can introduce here in NMR, and you can understand the peak without knowing the physics, the electron, what is the role of or moving of electron, spin quantum number, or etc. That is the beauty actually for NMR. You don't need to know so much of the physics. Only the spectrum itself self-explanatory if you understand the shielding effect. Okay?
Yes, ma'am.
Okay. So up to this for today. Then I will start from again little bit from the chemical shift, then go for the spin quantum split. Okay. So these are little bit complicated. This one, how to split the moieties actually the NMR spectra is like this. Okay. So this is NMR. CH3 proton and then CH2 proton. It's totally different. So very simple to understand. Okay. Here you have ethylene C, nitro, some propane. So how one proton is here? So one proton, and there is a 6 protons are here. Different. So this is NMR spectra. We'll see slowly. Lots of examples are there. So first we will understand the chemical. You have chemical shift and spin splitting first. This from this knowledge is basic knowledge. So you should understand these things, and then we'll go how this knowledge will help to understand the chemical, the NMR data, okay, or prediction of the NMR. Okay, so by now,
Thank you, ma'am.
thank assignment, okay, in time.
Thank you, ma'am.
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 Thank you, ma'am.